Pick up anything you say in the background, that's fine, whatever. All right, so limits of exponential and logarithmic functions. All right, so you will recall, either from last semester or long ago, an exponential function is the form y equals b to the x, where b is greater than 0. And we have these two graphs. So b to the x, where b is greater than 1, exponential function looks like so. And the graph of y equals b to the x, where b is between 0, looks like, it's always interesting because it's on a recording, right? I say it looks like so. So it looks like this one, and this one looks like that one. So just looking at the graphs, we just want to say, so use the graph above. What is the limit of b to the x as x approaches 0? 1, right? It's nice, it's a continuous function. What is the limit of b to the x as x approaches infinity? Infinity. And what is the limit of b to the x as x approaches negative infinity? Come on, look at the actual graph. 0. Okay, so that's when b is greater than 1. Now, what if we have b between 0 and 1, like 1/2, right? 1/2 to the x. Limit of b to the x as x approaches 0 is 1. The limit of b to the x as x goes to infinity is 0. And the limit of b to the x as x approaches negative infinity is positive infinity. In addition to that, we have this little table giving us the characteristics of any exponential graph. So the domain is set of all x such that x is an element of the reals. Very good. Whoever didn't say that, too bad. Or in interval notation, what would that look like? Negative infinity to infinity. And we know always to put a parenthesis, i.e. the round bracket next to an infinity, or a negative infinity. What's the range? So y is greater than 0, strictly greater than, or in bracket notation, 0 to infinity, this time with an open parenthesis next to 0, because we are not including 0. The x-intercepts are, there are none. The y-intercept is 1, and the horizontal asymptote is y equals 0. Vertical asymptote, there isn't one, but I know what you meant. Okay, next page. Oh, wait. What? Sorry, no pauses. State the value of each limit. Can you put a 4 in there? Is it okay to put 4 in there? Well, bad stuff. No. So you could just substitute a 4, right? So your first strategy in doing any limit, right, going right back to the beginning of February, is stick the number in and see what happens. Okay, so this is 3 to the 4 minus 4, which is 3 to the 0, which is 1. All right, well, bad stuff happened if I put a 0 in there. Yes. Here? Yeah, you can't throw a 0 in. Okay. So, if we are approaching 0 from the right, then what do we know about the number? It's going to be a small positive number, right? 0 from the right, small positive. What happens when you take 1 divided by a small positive number? You get a very large number. What happens when you take 4 and raise it to the power of a very large number? So this is 4 to a large positive hashtag. No, it's a number sign. In this case, it's a number sign. Use context. And 4 to a very large positive number will be positive infinity. All right. Coming at it from the left, what are we going to say about x? It's going to be very small negative. Okay. What's 1 over a very small negative? So it's going to be a large negative number. What's 4 to a large negative number? Negative. Oh my goodness. Yes, 0. Right? What is that? That's 1 over 4 to a large positive number. Right? Remember what a negative exponent does. Okay. What's 4 to a very large positive number? A very large number. What's 1 divided by a very large number? 0. Now, it isn't really, but the limit as it approaches. Okay. Get into the mode. You're going to need this a few pages down the line. All right, we've got the limit as x approaches -3 from the left. So what happens to this? So -3 from the left. Give me a number. What would it be? Give me like
1 over like no.
So just give me a number that's to the left of -3. So -3.001. So bigger than -3, right? In a sense of magnitude. So this will become -3.0001 plus 3, which is going to make it a very small negative. Okay. So what do we have? We have 1/2 to the power of 1 over a very small negative. What's 1 divided by a very small negative? It's going to be a very large negative. Okay, what's 1/2 to a very large negative? Still not quite there. So think about it. What would we do with the half? A half to a -1. So let's split out the negative from the large. What's a half to a negative? It's going to be 2 to a positive, right? So this will end up being 2 to a large positive number, which is not 0. It's infinity. Okay. I know it's going fast. Okay, you got all weekend to get caught up, right? Or, wait. Or rush into that. There's other ways we can look at these. Yeah, rush is one. Or, so let's look at it this way. This might help as well, right? So you could say, or, for this guy, let t equal 1 over x. Okay? This is the idea of replacing, right? We replace that. And then we say, what happens as x approaches 0? So as x approaches 0 from the right, what does t do? So t goes to infinity, right? If we take that down small, then t goes to positive infinity. And then what we're looking at now is the limit as t approaches infinity of 4 to the power of t, which anybody looking at that would say, well, obviously that's infinity, right? Which is equal to infinity. Okay, and then we can do the same thing. I'm just going to wipe these out because you already written them down. So same deal, right? We're just going to say, all right, let's do this a slightly different way. Let's let t equal 1 over x. Then as x approaches 0 from the left, what does t do? So we have 1 over very small negative, right? So t is going to approach negative infinity. Which means that we then have the limit as t approaches negative infinity of 4 to the t. And we can say, well, we're going to have 4 to a very large negative number, which is 1 over 4 to a very large number, which is 0, right? So this is going to equal 0. And similarly for d, we could say, let t equal 1 over x plus 3, and then say as x approaches 3 from the left, then t will approach negative infinity. And then we just do the limit. So now we've got x's out of there, we're just interested in t. So the limit as t approaches negative infinity of 1/2 to the 1 over t will be infinity. Okay, so it's just an alternative method of doing that. Okay, now we can turn the page. So now let's deal with logarithmic functions, right? State the inverse of y equals 3 to the x in exponential form. So to do an inverse, you interchange x and y. So this will become x is equal to 3 to the y. We don't like writing a function like that. We want to change it to y equals. So what's y equal to? Log base 3 of x. Okay, so logarithms. And as it says there, the inverse of y equals b to the x is y is equal to log base b of x. Remember, the base of the log has to be greater than 0, and if you're taking the log of something, that also must be greater than 0. And here's a couple of graphs. So we have log base b of x, where b is greater than 1, and log base b of x, where b is between 0 and 1. And we're just going to answer these guys. So as x approaches infinity, where's this going? Infinity. It's going to get there really slowly, but it will get there. And as x approaches 0 from the right, where are we going? Negative infinity. What happens if we approach 0 from the left? You can't, right? The function doesn't exist there. Use the graph above, complete the following. So, as if we're doing log base b of 1 over x, where b is between 0 and 1, as we approach infinity, we're going to go to negative infinity. And as we approach 0 from the right, we'll go to infinity. Okay? So far, so good. And then we have our characteristics of the log function. So the domain is it's x.
X is greater than
So x is greater than 0. Or 0 to infinity in interval notation. The range, y is null in the reals. Or in interval notation, negative infinity to infinity. The x-intercept, or intercepts. Is there one? Is there one? The y-intercept. And because the exponential had a horizontal asymptote, and this is an inverse, it has a vertical asymptote, which is x equals 0. We're just one page ahead. All right, and we're just going to do a few of these guys then. State the value of each limit. All right, can you toss a 5 in there? No, you can't put 5 in because you're doing the log of 0. We can't do a log of 0. So, what are we going to have? If we put, so approaching 5 from the right, what do we end up with here? So our descriptions are small positive, small negative, large positive, large negative. Okay, so we have a small positive number. So when we're looking at these limits, that's how we're going to describe things, right? Small positive, small negative, large positive, large negative. Okay. And then from then, we'll figure out. All right, so we will have, this will be equal to log base 2 of a small positive number. Okay, you got a small positive number. What is your value? Doesn't really matter that it's base 2. It can be base anything. Look at the graph. Negative infinity. Can we put in neg? Oh, or we'll do the or this time. Or let t equal x minus 5. And then say, as x approaches 5 from above, then t approaches 0 from above. And we will have the limit as t approaches 0 from above of log base 2 of t. So same deal, right? Either one works. The first one's probably just easier in a sense, right? Just sort of saying, well, what's the value, and then, okay, what's that going to be? The other one's more, well, it's cleaner, right? Because you're actually approaching a value, as opposed to say, oh, we get a small positive number. Right? Now we're saying this is going to. All right, B. So 4 from the left. So 4 from the left would be like 3.999999999, right? So what's 4 minus 3.99999? It's going to be a small positive. Which means, but the base is a half. So what happens? So it's log base 1/2 of a small positive number, which is equal to, flip back, look at the graph. Oh, flip back. It's above you. Yeah, where's it? It's going to infinity, right? Yeah. Or, right, same deal. Let t equal 4 minus x. As x approaches 4 from the left, then t approaches 0 from the right. Okay, that's going to be the small positive. So it's going to be, t will be the small positive. And then we can say the limit as t approaches 0 from the right of log base 1/2 of t is equal to infinity. So either way, right? Whatever speaks to you. State the domain of log base 3 5 minus 2x. Oh, it's like a 30-1 question. Actually, it is 30-1. So what do we know? That means 5 minus 2x has to be greater than 0. So negative 2x will be greater than negative 5, and x will be greater than 5/2. And then you correct my error. Less than. I know. See? So that's one of those on purpose. Okay. So because we're dividing both sides by a negative, then we're going to reverse the inequality sign. Okay, so set of all x such that x is less than 5/2, or in interval notation from negative infinity to 5/2. Going good? Good pace. Right? Yeah. Shout out to Jake, who wanted to be here when a recording was made, and I said, no, there's nothing to be recorded. Then it turned out this one had to be. So you got to mention Jake. Just don't watch the lesson last night. Watch it this weekend. You'll see and hear yourself. So use the fact that y equals b to the axis. So convert from exponential to logarithmic. So 2 cubed equals 8 becomes log. What's the base? Of equals 3. Right. What's a logarithm? It's an exponent. You're supposed to all say that. Come on, it's being recorded. You all together, right? A logarithm is an exponent. Thank you. You can all list that. It's at 17 minutes and 48. So if you're curious, you want to pop in there and hear that. And if I have log base 3 of 1 over 81 equals negative 4 in exponential form, what's the base? What's the exponent? What's that equal to? There we go. And note that that's that. Evaluate. Okay, you should do this while I just pause the recording. And there are the answers. So, either pause the video here so you can look at the answers because they're about to disappear. And we didn't show you how to do this because you wouldn't have made it this far. Laws of logs. So a little bit of laws of logs. So the log of a product is the sum of the individual logs. The log of a quotient is the difference. The log of a power is the one really useful law of logs, right? It's the one that allows us to solve for that unknown exponent that we had to do by graphing up until 30-1. Hey, actually solve this. And if you were to expand log base 3 of x squared y 9z, then we just use these laws. So we say, all right, so that's going to be equal to log base 3 of x squared. What do we do with the y? Plus, because it's a multiply, right? So plus log base 3 of y. And what do we do with the 9z? So minus log base 3 of 9z. Okay, so that's a good starting step. Then we're going to kick the 2 out front, so it'll become 2 log base 3x. We're not going to do anything with the log base 3y because it just is. And then we're going to go minus. We're going to say, wow, we got a product here, right? So we're going to have to split this product up. So we're going to go minus log base 3, 9 plus log base 3z. And then I'm just going to work it out. What's log base 3 of 9? 2. So 2 log base 3x plus log base 3y minus 2 minus log base 3z. You know, or something to that effect. Those 4 terms with the appropriate signs in any particular order. All right, so just keep these in mind because later on you're going to see answers and it won't be the answer that you got. Like you'll have got some answer and there'll be logs, you're looking at that and they're not the same and they really are the same. It's just split out or not split out. Okay, so whenever you see an answer that doesn't look like a multiple choice answer, just look at yours and say, do I have the same as one of these but just in a different form? Okay, so am I looking to change the form? And let's put it all together. So what's the start? Why was there a jump? Okay, so we start with log base 2 of x cubed minus log base 2 of y minus, so ultimately, what do we got? So x cubed over y to the 4th. Where does the z go? Underneath. Okay, so y to the 4th z. Okay. You can also do tricky stuff like this. Right? That's why the y to the 4th and the z are together. They're prime and the minus. Evaluate. Step 1. Oh, well, what can we do here? Oh, maybe when we get it all together, they're all, yeah. So if we get it all together, maybe it'll come out something nice. So what do we got? We got log base 3 of 144 to the 1/2 minus log base 3 of 4 plus 2 times 3. Now you're looking at the 3 and you're going, oh, yeah, okay, right, got it. Everybody got it? 27 is, okay. So what's 144 to the 1/2? Yes, we expect you to do that without a calculator. 12. Yeah. Minus log base 4, 3 plus 6, okay, which is log base 3 of, no, it's 4. No, that's a 3. Hang on. Clean up an aisle. So 12 over 4. 7. I don't want to drag it out any longer. Okay, you could write log base 3 of 3 plus 6. Oops. Everything shifted. Hang on. We can't leave a mess. Okay, good. Solve. Express your answers in exact. What is this? 30-1 again? What are you doing? Why are you doing this? Who put this stuff in there? It's not. Yeah, I know. Why? Why? All right. How do we solve for an unknown exponent? Take the log of both sides, right? We'll do this the long, painful way because we should at least just see what it is we're doing here. So we have the log of 5 to the x is equal to the log of 6, and then bring the x down. So it becomes x log 5 equals log 6. And so x is equal to log 6 over log 5. which could also be written how? So log base 5. So if you think of base change formula, right, that's same as log base 5 of 6. Why do we write that? Well, who knows? Maybe the answer looks like this. Or not, because it's gone. So maybe the answer is just this. Control Z twice should take care of that. Okay. So maybe it's log 6 over log 5. Maybe that's what you have. You're looking for it. It's not there, but there's a log base 5 of 6. You go, oh, okay, wait, those are the same. Okay, so what do we do here? No, what matters more is if it's a multiple choice, what form is the answer? If you wrote log 6 over log 5 or log base 5, 6, I'm good with either one. Okay? What I'm more worried about for you guys is if it's multiple choice and it's in this form, you just need to be able to say, I got this. Oh yeah, that's that. So, same deal. Take log of both sides. What does this side become? 2x plus 3 log 4. What does this side become? 1. Right. This is log 10. What's the base on a log when there's no base on the log? It's base 10. Okay. All right. So there are about 600 different. Okay. Now there's about 3 or 4 different ways this could be written. Again, same deal, right? Why would you write it in different forms? Well, it depends what I'm looking at for an answer. So what could we say? Well, we could expand this. 2x log 4 plus 3 log 4 equals 1. What's 3 log 4? It's just a number, right? It's 3 times whatever exponent you raise the base 10 to in order to get a 4. This is just a number, so put it over with the numbers. So 2x log 4 is equal to 1 minus 3 log 4. So 2x is equal to 1 minus 3 log 4 over log 4. And x is equal to 1 minus 3 log 4 over 2 log 4. Okay, and then there's many variations of that. Okay, so you can't divide out a log. Log is an operation. It's not a. It's a log 4.
Yeah, 2x.
Oh, divide the log. Yeah. So go 2x plus 3 equals 1 over log 4.
Yeah.
Okay, so alternative B. What do we got? 2x plus 3 equals 1 over log 4. 2x is equal to 1 over log 4 minus 3. X is equal to that I don't know. It's kind of bad, right? Like that. So, all right, let's just move that 2 in. So let's just divide everything by 2. X is equal to 1 over 2 log 4 minus 3 halves. Alternative B. Okay, so there's many different forms, right? Just be aware of that. I could leave the old video up. I think we did about 6 of them in the old one. Okay. So again, right, one of the keys to this is just because your answer isn't in the multiple choice doesn't mean that your answer isn't in the multiple choice. It just means it might be a different form. So what I would do on a test, I kind of leave that, go on and do other stuff, then come back. If time's running tight, pick the thing that most likely looks like it would probably transmute into. Okay? Otherwise, if you have time, then try moving around. Use change of base formula. Yeah, so you can't do this one. But the base change formula says what? Log base 3 of 20 is equal to what? Yeah, log 20 divided by log 3, which is about 2.73. Okay. Good? Okay. Now we get into the actual kind of new stuff. So what is E? We're actually going to flip ahead a couple of pages because I want to introduce it a little more intuitively as opposed to, kind of, you know, what they do here is they just say stuff and then they say stuff there and then, okay, I want to go here. Let's talk money. because everybody understands money, right? So what is this thing E, and how does it relate to money? So we got a compound interest formula, right? A equals P times 1 plus R to the N. R is the interest rate per compounding period, N is the number of compounding periods, P is the principal or the initial amount, and A is what you're going to end up with. So E relates to growth, continuous growth at a rate of 100%. So if we got 100% interest for 1 year, how much money will we have at the end of the year? You got $1, put it in the bank, get 100%. At the end of the year, you have $2. All right, so if we're going to write this out with a nice little formula, right, we'd say A is equal to 1 times 1 plus 1 to the 1. You got $2. All right, what if we paid semi-annually? What if we gave you the interest twice a year? You no longer get 100%. So if you think about the interest, the 100%, right? It's like somewhere else this money is building up, right? And then at the end of 1 year, magically, at the end of the 365th day, it's like, bing, it drops into your account. So your account goes from $1, jumps to $2, right? What if we do it semi-annually? Well, the amount I'm going to end up with is $1 plus. So I'm not going to get all the interest twice a year. I'm going to get half the interest rate, 1/2, right, 50%, 0.5, twice a year. And how much money will we end up with? So it's going to be like 1.5 squared. And those of you who know how to square numbers ending in 5, it ends in 25, multiply the number by the next higher number. For example, 45 squared is 2025. Okay, so this is $2.25. Okay, cool. Hey, that's better than the $2, right? Why? Because 6 months in, we got 50 cents. And now that dollar kept earning its interest, but then the 50 cents started earning its own interest, right? And then that all got paid out at the end. All right, what if we do this 4 times a year? So so we still got the dollar. Okay, I'm not getting 100%, right? I'm getting 25%. I'm getting 1/4 of the interest, but I get it 4 times a year. So, I've done the math so you didn't have to. We get $2.4414, etc. Got $2.44. All right, this is looking better, right? We started at $2, so we got 2 1/4. Monthly. So monthly, how many times would you get paid if it was monthly? So you get paid 12 times, but you're going to get 1/12 of the interest rate, right? 1/12 of 1. Remember, that 1 is a percent. As a percent is 100%. That 1 is a decimal. All right, so we got 1 plus 1/12 to the 12th, and we're going to get 2.613035 ... All right, what if they paid me every millisecond? We're not going to go there just yet, but how much money would I end up with if they paid me like almost infinitely, right? Every millisecond for a year? Well, you just know something. Would you get like $3, $4? It's going to grow up and be like $500,000, $100,000, like $1 million at the end of a year. So, okay, let's see what happens. So let's say we go weekly. So weekly, you get 1/52nd of the interest every week, but you get paid 52 times a year, right? You have little chunks of money, each earning interest, right? Which all adds in every month. It gets added in. And that equals 2.69259695 All right, daily interest. What if you got paid every day? 365, right? Unless we're doing this last year, that'd be like 366. So a lot of bank accounts do advertise daily interest, right? So they're going to calculate. So you're going to get 1/365th. That's your interest rate, right? This one here just keeps the original 1. This is your added interest. At the end, you get that final amount paid. And that'll be to the power of 365. So what's that? It's got to be like $27. So $2.71. And there's a 4, 5, 6, ... Predict the value. All right, what if you got compounded every second? Well, we can see that hey, we went from 2 to 2 1/4 to 2.44. It's growing, but it's slowing in its growing. Okay? And so every second per year, here's the number. 2.718284773. So there's a limit to this continuous growth. The limit of continuous growth. So we're getting 100% growth rate, right? And it's growing continuously. The limit is E, which is 2.718281828459145235336. Keeps going. All right, so there's a limit. You're not getting any more than $2.72 rounded, no matter how often we pay you interest. Okay, it could be a billion times in a year. All you're going to do is get closer to E. So that's what E is. Okay, and now we'll go back to what is E? Asked there, but then just present it as kind of like, hey, it's this number. So we're going to go back. What is E? Use your graphing calculator to determine the value for each limit rounded to the nearest hundredth. Okay, so we do that. I'm just going to pop into decimals. All right, so we have, what's the equation? I'm going to go b to the x minus 1, b to the x minus, oh, I'm going to have to throw brackets around that. Hang on. So bracket b to the x minus 1 all over x, oops, divided by x. Add slider b. So I'm going to put b in there so we can change it, right? So here it is, right? If b is 1, okay, that's pretty boring. So what if b is, what do they say, 2? Okay, so if b is 2, then what do we get? What are we looking at? Oh, so we wanted what? The limit as h approaches 0. So for us, the limit as x approaches 0. We want to know what's this value here. So what is that value there? So, but, yeah, right? See, it's undefined at 0, right? Okay, so it works out to be 0.69. So 0.69. What if we make b 2.5? So we go there, 2.5. And then we get value of almost 1, right? Like not quite. So 0.91. 0.91. What if we do it for b equals 3? So over here, 3. And we get a value of a little over 1 there, right? So like 1.10 is what, if you were on a calculator, 1.10. Now, there's a value of b that exists so that the limit as h, we were using x, approaches 0, b to the h minus 1 equals 1. We call this value e. That is, e is the value such that the limit of e to the h minus 1 over h is equal to 1. Determining the value of e rounded to the nearest hundredth. So then in this case, we would actually have to put the value of e in there, right? Now, on a calculator, you could play with it, but if I go 2.72, which is to the nearest hundredth, then we can see that this value is going to get closer to 1, right? 0.991 and undefined 1.006. So to the nearest hundredth, that's 2.72. Okay. So that's E. I just think that's a crappy way to introduce E. It was some number where you have the limit of whatever, right? It's the limit of growth. It's if you pay me 100% interest and you pay me infinitely, it's going to get to E. Okay. What is ln x? Well, what's the inverse of e to the x? It's going to be x is equal to e to the y. which can also be expressed in logarithmic form as log base e of x is equal to y, right? Or y equals log base e of x. I guess would be a better way. Y is equal to log, the base is e, and the value you're going to get is x. This comes up pretty often. So you're not going to see log base e of x. You're going to see y is equal to ln x, which is read as ln or ln. Okay, either one is acceptable. So you could say ln, lends itself to a nice joke, which we'll do later on, or you could say ln. And it's called the natural log of x, right? Because again, e is the natural limit of growth. Okay, so anytime from you're going to run into e, you do some post-secondary stuff. Anytime something is growing, so you go into sciences, biology, there's things growing, there's populations growing. You go into finance, money, it's growing, hopefully. Okay, money is growing. Anytime that there's growth, continuous growth, right? Now remember, e takes 100%, but you can just do e to some power. It's going to be e to some power, right? We're going to get y equals e to the x. Y equals e to the x is like y equals 2 to the x, right? Only the base is e, that 2.718281828. It's an exponential growth function. Okay? So you can adjust, if you adjust that, you can adjust the rate at which the growth occurs. So in other words, blah, 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 and the log functions, they're inverses of each other. Sketch them. I mean, honestly, it's just like sketch an exponential function, sketch a log function, where the base is greater than 1, so. Right, so that's y equals e to the x, i.e. any exponential function ever, right, because it's just a sketch, and then this is any exponential function where the base is greater than 1, really. And logarithmic, same deal. Any logarithmic function where the base is greater than 1. Okay, that's what those look like, right? But then we're going to use that. If not on the next page, then on the page after that. We're going to use that just as we did where we had like 3 to the x or something, right? Other expressions of, so this kind of, have you seen sigma notation before? Yes? Okay. When? In 30-1? Did we do it in 30-1? No? Yes? I don't know. Okay. Sigma notation, also known as summation notation. So for those of you seeing this for the first time, it's just a shorthand way of saying, I'm going to start with n is 0, and I'm going to go up to k, whatever k is. So if we do this, the sum as n is equal to 0 to 3 of 1 over n factorial, bless you, that will live forever on YouTube at 43-ish. That's me sneezing. Okay, so what you do is you start with n is 0, so you go 1 over 0 factorial, and then you increase n by 1 each time, and you're summing, right? It's summation. So you add, and then you increase n by 1, so it now becomes 1 over 2 factorial, plus 1 over 3 factorial. And then you can evaluate those, right? Which would be, so 0 factorial is 1, so it would be 1 over 1, plus 1 over 1, plus 1 over 2, plus 1 over 6, which is 1 plus 1 plus 0.5 plus 0.16 repeating, which would be like 2.6. Sorry, 2.6 and then a 6 repeating. 2.6 and then the 6 repeating. Right, like if you had a calculator. Or, if somebody... Okay, so here's this expansion, right? So each one is just a line. This would just be, for n is 0, this would just be 1 over, you got 1, right? And then 2, 2.5. Where do we see those numbers? It was like the $1, $2, 2, and so on. And you can see that, so for 3, this would be the 2.6 and then the 6 repeating. If we do it 4 times, 6 times, 2.718, okay, and then we start getting down here. And I went up to like 17 times, because this number starts to get pretty big, right? Like 17 factorial is 3.55 times 10 to the 14th. So we're up into the hundreds of trillions there. And then 1 over that tends to get pretty small, right? So these guys are just getting smaller, 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 right? Like there's 1, and then there's 1.5. So we get to 2.5, then we get to 2.6, and we add little bits each time. We have 2.7182818284590. That's just rounded because it goes 4, 5. 2, 3, 5, 3, 6. I'd go on, but I can't. I only know 20 decimals for E. Okay, but you can see that that's kind of interesting. Like, what's that got to do with like interest rates? Right. Look, this is just an expansion of. If you add up sums of 1 over n factorial, and basically, if you just took the limit as n went to, well, this says from 0 to infinity. Right? You kept adding that up. You're going to get E. Determine the following limits graphically. So x plus 1 over x to the x. That's what we did with the interest rates, right? 1 plus 1 over 365 to the 365. Okay, yeah. Somewhere I have that here. Yeah. Oh, wait. No, it's up here. So first, we're going to make that disappear. Okay, there's the graph 1 plus 1 over x to the x. Here's the graph here, right? And you can see it's climbing away. And here's 2, and so here's 3. So if I zoom that out, and out, okay, well, that's maybe a bit too far, because it's 1, 2, 3, you can see, and we can trace the values, right? But, I don't know if you can see them. 2.664 and climbing, right? And that's just out at 25, right? We went to 365 and so on. So what's that limit? E. And 1 plus x to the 1 over x. So what if you do it this way? So I have that graph as well. So we'll get rid of that graph. And what's that coming down to? Oh, this happens above. Oops, sorry. No, we want the limit as x approaches 0. So what happens as we get close to 0? 2.705. Now with 0, of course, we're undefined, right? 2.82. So also E, right? This time it's a limit. So this is the limit as x approaches infinity. This is the limit as x approaches 0 of this. And that's E. Don't write this down. Like, of all the numbers to memorize, like 2.7, 1828, 1828. So once you got 1828, you just say it twice. 45, 90, 45, 2, 35, 36. That was like not hard to remember, really. Okay, we did this, right? So now we just got a little fill it in the blanks, and we'll be done. Just think of e to the x and ln x. I guess I was going to write them on the board, but I suppose we should put them here. Y equals e to the x. Y equals ln x. Okay, as x approaches infinity, ln x is going to go to infinity. As x approaches 0 from the right, ln x, negative infinity. As x approaches 0 from the left, ln x, not exist. There's arguments about that. I'm not going to show the webpage because I didn't bring it up, but there's arguments about, and this would be for 3rd or 4th year math when you're in university, arguments about, does that not exist, or does the limit as x approaches 0, right? Because here we would say the limit as x approaches 0 does not exist, because we've got infinity and then we've got does not exist. And the argument is based upon, well, if you say the limit as x approaches 0 and the thing just doesn't exist over here, we're not even going to consider that. We'll restrict our domain. And other people say, no, you can't do that. So just so you know, it's still up for grabs as far as that goes. All right, limit as x approaches infinity of e to the x is, I'm short-ish. And the limit as x approaches negative infinity of e to the x is, and the limit as x approaches 0 of e to the x is 1. Right? 1 and done. Yeah. Because you can evaluate that. What's e to the 0? Anything to the 0 is 1. Then there's the argument about 0 to the 0, but let's not go there. All right, state the value. Why is my watch restarting? What time is it? How much time do we have left? 15 minutes. Oh, easy, easy. Be through this. Okay, so we do this kind of the same way we did the earlier one about thinking about what's. This time we're just going to think, we're not going to do let the t equal this or anything. We're just going to kind of think about this. Okay, so x goes to infinity. We're going to subtract 1 from that. So we're going to raise e to the power of 1 less than some concept, which isn't a number, which is going to give us what? So this is a really big number, but then we're going to add 2 to it. So we really have what? Infinity plus 2, which is just what? Okay. So x is big, huge, huge. X is huge. You subtract 1 from it, it's still huge. Raise e to the power of a really big number. You get a really big number, and then add 2 to that, right? No. Okay. Limit as x approaches negative infinity. All right, so now we've got this really big negative number. And then we're subtracting 1 from it, so it's an even bigger negative number. So you're raising e to a large negative, which becomes 1 over e to a large positive, which becomes 0. And then you're going to add 2 to that. You're going to get 2. Okay, so just to recap, we have e to large negative, okay, which is 1 over e to large positive. So this just gets zeroed out, and then we just have a 2. Okay. Next one. X approaches 3. All right, can I put a 3 in there? 3 minus 3 is 0. What's e to the 0? So it's 1 divided by 1? 1. All right. What happens if I put a 3 in there, but this time I square it? It's the exact same thing, right? 3 minus 3 is 0. 0 squared is still 0. E to the 0 is still 1. And 1 over 1 is 1. Okay, limit of 1 over the root of e to the x minus e to the root of x minus 3 as x approaches 3 from the right. So we're going to get e to the square root of a really small number, which is going to be what? Still a really small number. Okay, wait, where are we approaching from? 3. Wow. Yeah, from the right. Okay. I reversed my key here. So this will be 1 over e to the root of small number. Small positive, right? Small positive number. Which is, so a small positive number is basically 0. E to the 0 is 1. 1 over 1 is 1. Okay? So we're just getting to the point of just thinking about it. Now on a test you can write that. You just write e to the root of a small positive number, if you like. What's this guy going to be? So now we're approaching 3 from the left. So to the square root of what? Small negative. What's the square root of a small negative? You can't do that. I don't even have the you can't do that thing. I know. Missing a lot of opportunities. Okay? So you cannot take the square root of a small negative number. You cannot take the square root of a negative. Okay, x approaching 2 from below. So all I just think of is like 1.99999, right? If I square that, how does it compare to 4? Less than 4 or greater than 4? Yeah, it's less than, right? So it's smaller than 2. Its square is going to be less than 4. We're going to have the ln of a very small positive number, which is? Very small positive number. Okay, so the ln of a small positive is negative infinity, right? All right, what if you come at 2 from above? Then when you square it, it's going to be a little bigger than 4. And you're going to have the ln of 4 minus a number slightly bigger than 4, which will be what? The ln of a small negative. What's the ln of a small negative? It doesn't exist. Right? You can't even do the ln of 0, let alone a small negative. Right? You can do a small positive, that's close to 0. Okay, again, all you're doing is just thinking about the graphs, background, just these guys here, right? You're just looking at these guys here and saying, all right, what's going on? All right, what do we got? 4 more? Negative 2 from below. No, sorry, from the left. I would say from below. Should be saying from the left. Negative 2 from the left. Give me a number to the nearest tenth that's below negative 2. Sorry, that's to the left of negative 2. Like negative 2.1. So when I square that, I'm going to get a positive number bigger than 4. So I'm going to have 4 minus a number that's bigger than 4, which will give me the ln of a small negative, which we already did. Minus number bigger than 4. Okay, so you're doing the ln of a small negative. Ln of small negative. I tend to call it ln. Those of you who are fans of a certain TV show can certainly call it ln. All right, negative 2 from the right. What's the nearest tenth to the right of 2? Negative 2, sorry. Negative 1.9. When you square that, you're going to get a number smaller than 4. So you got 4 minus a number smaller than 4, which is small positive, and the limit will be, okay, so that's going to be the ln of 4 minus positive number less than 4. So you're doing the ln of a small positive, right, which is negative infinity. All right, 2 more. My watch is restarted. X approaches pi from the left. All right, hang on. I need. Okay, wait for it. Show me a sign. Now, this one I just made up right now. Show me a sign. Okay, so let's look at, here, there we go. So, there's pi. We are approaching pi from the left. That's here. So we're coming at it this way. What is the sign of x going to be if we're approaching pi from the left? It's going to be, it's going to approach 0, but on its way there, it's going to be a very small positive. So this will be the ln of a very small positive, which is negative infinity. All right, we are approaching pi from the right. The sign of pi will be a very small negative, and the ln of a very small negative does not exist. Less than 59.5 minutes. Right, so ln small negative does not exist. Done.